Next, we look at the relationship between the first and second derivatives and properties of the graph of the function. In particular, when is the function increasing, when is it decreasing, when is it concave up, when is it concave down, and how are those features related to the sign or properties of the first derivative and the second derivative. So a quick review, I'll just draw a picture. So a function is increasing, it's going to look like this. So this is an increasing function. And then when a function is decreasing, it starts high and it's always moving downward. So for a decreasing function, if you have x1 and x2, x2 is always less than x1. Whereas for an increased function, or f of x2 is less than f of x1. For an increasing function, the output at x2 is always greater than the output at x1. So this is the increasing and decreasing. Now, how would the derivative be related to whether or not the function is increasing or decreasing? Well, if the function is increasing and we draw the tangent line like that, notice that the tangent line, I'll draw 3 of them at 3 different points, always has a positive slope, right? Because remember, the tangent line, whose slope is equal to the derivative, tells you the change of y over the change of x. Well, if a function is increasing, you always have to get a positive change of y for a positive change of x. So if you change your x by a small amount, you should see a positive change in y. So the slope has to be positive, which means the derivative has to be positive. So for increasing function, f prime of x is greater than 0. Now it's possible to have a function that is increasing and then decreasing. Right, so we would say it's increasing, let's say from 0 to 5, and then it's decreasing from, let's say, 5 to 10. Right, so in this case, we would say that the derivative is positive from 0 to 5. And then from 5 to 10, the derivative would be negative. Right. So similarly, if we look at the tangent line for a decreasing function, that's supposed to be attached there at a couple different points, we see that it always has a downward slope, right? So by the same reasoning, the delta y, if you take a positive delta x, your delta y will have to be negative. If your function's decreasing, delta y is negative. So delta y over delta x will be less than 0. Right? So for the decreasing function, f prime of x is less than 0. Right? So it's pretty easy to remember. If the function's increasing, it's a positive rate of change, so the derivative is positive. If the function's decreasing, that's a negative rate of change, so the derivative is negative. So increasing, derivative positive, decreasing, derivative negative. So next, let's look at concavity. So a reminder, so we'll draw 2 shapes. So here we have a function that looks like this. And here we have the function that looks like that. So these are the archetypical concave up, concave down. Now it doesn't have to curve. You can have something that looks just like that, and the levels up. That would be concave up for everything you see. It doesn't have to actually bounce all the way back up. But anything with this general shape about it is going to be concave up, and anything with this general shape is concave down. So if you analyze this a little bit deeper, let's look at some tangent lines. So here we have a point, I'll draw it in red. And the tangent line is like that. Hard to see. Here the tangent line is just like that. here the tangent line is like this, here the tangent line is like that. Okay, then for concave down, the tangent line here is like that. I'm doing a better job drawing them over here. The tangent line here. You just surgically remove this little piece. Tangent line here is like that. Tangent line here is like this. So while I'm drawing this, pay attention. Do you notice anything? Right. So if you're concave up, the graph in a neighborhood of any point is always above the tangent line. So if you look at all these tangent lines, the graph ends up being above it. So we can define concavity at a point. So at a point, we have a function and its tangent line, so it's supposed to be tangent. So if in a small neighborhood about that point, so if this is our point here, if we look in a small neighborhood about that, the function's concave up if the graph is always higher than the tangent line. So you have something like this, and then if it's concave down, it's the opposite. So for a graph to be concave down, it's always lower or less than its tangent lines. And for a graph to be concave up, it's always above the tangent lines. So basically, that's just a technical way of saying concave up is a smile and concave down is a frown. Now, how does this have to do with derivatives? And I'm going to just start out my graph over anew. So let's do a concave up function. Nice function like that. Now notice that concave up. Notice a function can be concave up and decreasing or concave up and increasing. So a function can be, if you say it's concave up, it can still be increasing or decreasing. Same thing with concave down. If you say it's concave down, it can be still increasing or decreasing. If you say that the function's increasing, it could be concave up increasing or concave down increasing. So these are completely independent. So one, increasing would not, you can have increasing concave up, increasing concave down, or vice versa. So when we look at these tangent lines, we have a strong negative slope, say maybe minus 10. And then we have another negative slope, maybe minus 8. Then the negative slope is shallowing out, minus 6. Maybe here it's minus 3. Maybe here it's minus 1. Here the slope is 0. So the derivative, the values, remember the slope of the tangent line is equal to the derivative. So the derivative was minus 10, minus 8, minus 6, minus 3, minus 1, 0, 1, 3. Maybe the slope over here is 8. Maybe the slope up here is 10. So what do you notice about the values of the slopes? The slopes keep increasing, right? So for concave up, if it's decreasing at a smaller and smaller and smaller rate. So that decrease starts off at a large rate and it's decreasing at a slower and slower and slower rate. If it's increasing, it will be increasing at a greater and greater rate. So concave up, so if it's decreasing, it's doing so at a slower and slower rate. Meaning those large negative downward slopes are becoming less negative. They're becoming less large. Negative 10 is going to negative 8, going to negative 6. If it's increasing, it increases at a faster and faster rate. Right? It's increasing at a rate of 1, then a rate of 3, then a rate of 8. So if a function's concave up, f prime is increasing. Because remember, the value of these slopes of the tangent lines are the values of the outputs of the derivative. So a function is concave up exactly when its derivative is increasing. Conversely, it's concave down when the opposite of all of this is true. So a function's concave down when its derivative is decreasing. So concave down, something like this. Large is increasing with a high slope. It looks like 30, maybe 20. Maybe this is 10, 8, 3, 0, -3, -5, -20, -30. Some, whatever the case might be. So for concave down, it's increasing. It increases at a lesser and lesser rate. Whereas concave up increased at a greater and greater rate. In other words, concave up increased faster and faster. And it decreases at a greater and greater rate. So -3, -5, -20, -30. So it's decreasing faster and faster. Whereas concave up was decreasing at a lesser and lesser rate. So finally there's a nice chart that I like to use. So I like to put f, f prime, f double prime. So this chart is very useful in a variety of just different problems. So if the function f is increasing or decreasing, then we can say concave up or concave down. What can you say about the derivatives? So if a function f is increasing, its derivative is positive, and if the function f is decreasing, its derivative is negative. And then there's no information about f double prime. So here we just, no information. It could be anything. Now, if a function is concave up, we said that it's increasing at a greater and greater rate, or decreasing, concave up, increasing at a greater and greater rate, or decreasing at a lesser and lesser rate. Either way, the derivative was increasing. So concave up means that the derivative is increasing. Concave down means the derivative is decreasing. Now, the derivative itself is a function, and this function has its own derivative. So if we say that f prime is increasing, f double prime would have to be positive. If we say that f prime is decreasing, f double prime would be negative. We're just applying this rule up here to the function f prime down here. Similarly, if you said that f, the fourth derivative was increasing, that means the fifth derivative would be positive. If the fourth derivative was concave up, the fifth derivative would have to be increasing, and the sixth derivative would have to be positive. So these are it's just a general chart, and occasionally you might want to apply them to various contexts. But if you have whatever the original function is, and whichever function you're analyzing, when it's increasing, its derivative is positive. When that function is decreasing, its derivative is negative. When it's concave up, the derivative is increasing, and the second derivative is positive, and so forth. So this is also very useful in drawing graphs of functions that you might not know what they look like, because we can look and say, okay, well, let's look at the derivatives of a function. So if you want to graph a function, this is the old way of doing it, graph a function, you look at the derivatives. Look at the derivatives. So you identify the intervals on which f prime is positive and negative. So you set up the x-axis, f prime is positive here, negative, positive, negative. So the function must be increasing, increasing, decreasing, increasing, decreasing. And then you do the same thing with the second derivative. So there's f prime, f double prime. Concave up and increase, so it's concave up and increasing, concave down and increasing, concave down and decreasing, concave up and decreasing, concave up and increasing, concave down and increasing, and so forth. So you basically look at f prime, you look at f double prime, and you just say, where is f prime positive, where is f prime negative? Where is f double prime positive, where is f double prime negative? And you make a chart like this. And you say, okay, where, and you just list what you find out. And then you look at, okay, if the function's increasing and concave up, it's going to look like this. If it's increasing and concave down, it's going to look like that. If it's decreasing concave down, it's going to look like this. If it's decreasing concave up, it looks like that. And you just match up this so you get basically an idea, a qualitative impression of what the graph looks like. So you'll see the actual trends of the graph by just looking at the sign, whether it's positive or negative, of the first derivative and the second derivative.